Hello again, APChem students. This is Lou Akampora from Advanced Kentucky, and I want to get right into a short video, I hope, about electrolysis and electrochemistry. Some of you may have looked at the short video, not so short video actually, on galvanic cells and know a little bit about electrochemistry from the spontaneous perspective. Today we're going to turn that around and look at electrolysis and what might happen and why it happens and how it might happen. So let me remind you that electrochemistry is always going to be based on electron transfer or redox reactions. And if you have a table of standard reduction potentials, and I've reproduced an abbreviated version of the table that you may have in front of you in the notes here. And the table of standard reduction potentials lists half reactions, again, because they explicitly include electrons, in order from usually the highest potential at the top to the lowest. And this is really a measure of how strongly the species at the left attracts electrons, or multiple species sometimes, to become the species at the right. So fluorine would be the strongest electron accepting species. Sodium ions would be the weakest on this table, and conversely, sodium atoms would be most willing or most eager to lose electrons, whereas fluoride ions really would not have much of a tendency to lose electrons. And that correspond to your impressions from atomic structure. So when two half reactions are combined to make a full reaction, we've always got to flip one of them around. We can't have two reductions occurring at the same time. And traditionally, in a galvanic cell, we'll be harnessing a spontaneous reaction to drive an electric current and therefore produce work or get work done. So let me remind you and review a little bit of a galvanic cell. Let me just pick two half reactions here. The bromine plus 2 electrons becoming 2 bromide ions, and copper 2 ion gaining 2 electrons to become copper atoms. And how might we set up a galvanic cell using these two half reactions? So let me kind of sketch one out here on the board. We'd have a 1/2 cell that would have some copper ion, possibly a solution of copper sulfate or copper nitrate. And if it's going to be standard concentrations, I would have a concentration of 1 mole per liter. We would immerse a metallic copper electrode in there, and nothing will happen in that half cell. That will be this half reaction. In the other half cell, we might have a solution, and now it's got to contain both bromine and bromide. So we'll put a solution here, Br2. Now bromine is a halogen. It is naturally occurring as a liquid, a pure liquid. It dissolves not very well into water, and you might review your solubility principles, since bromine is non-polar and water is quite polar and forms hydrogen bonds. It won't dissolve very well, but it does dissolve sufficiently that we can have some bromine in a saturated solution. We would also need some bromide ions. There might be a solution of sodium bromide in there. And this would be our other half cell. To generate a cell, we would need to connect these two half cells, and we'd use a conducting bridge, a wire rather, first a wire, and I'll put a resistor in that wire directly connected to the copper electrode. And over here, well, we're not going to want the wire to dip directly into the bromine solution, because if this wire is made of copper or iron, it would react with the bromine. So we usually use an inert surface. We can use graphite, which is conductive and doesn't react. I like to use platinum since it's shiny and expensive, and platinum is a noble metal which won't react. And I'm going to put a switch here in our circuit so we can control the flow of electricity. Right now, nothing would happen. No cell reaction would happen because we don't have a complete circuit. So most of you would know to complete the circuit with a salt bridge. That might be some inert ions. Let's make this potassium nitrate, K plus, and NO3. We now have our galvanic cell, And we could use this if we close the switch to drive a current. In what direction would that current go would be a pretty fair question, and now we'll look at our standard reduction potentials. Since bromine has a higher reduction potential than copper ion, this one would be flipped around. The actual reaction half reaction that would occur over here would be copper atoms losing 2 electrons to become copper ions. In this half cell, the reduction half reaction would occur, and we would see bromine molecules gaining 2 electrons to become 2 bromide ions. I could combine these two half reactions directly, and since in this particular case the same number of electrons appear in both the oxidation and the reduction half reactions, they'll cancel, and I will get copper atoms reacting with bromine molecules to form copper 2 ions and 2 bromide ions. You can see that electrons, once this switch here is closed, electrons would flow left to right through the wire, through the conducting wire. Positive ions would also flow left to right to complete the charge, or to neutralize the charge, complete the circuit. Negative ions flowing right to left. And I would measure an ideal open circuit potential here. If I had a voltmeter here, my voltmeter would read 1.09 volts minus 0.34 volts, just the difference between those two standard potentials, and that works out to 0.73 volts. I could also put in an ammeter here to measure the current in coulombs per second, and if I measured the current and the amount of time that current ran, I would know how many coulombs of charge were passed, and I would convert that to, or you would convert that to moles of electrons, and then by using the stoichiometric relationships, you would know how many moles of bromine were consumed, how many moles of bromide ion were formed, how many moles of copper metal were consumed, and how many moles of copper ion were formed during that time. And that is a galvanic cell. Not a very practical galvanic cell, but certainly one that you can build in theory. I promised we'd talk about electrolysis today, and I want to see what would happen now if instead of having a resistor here, or a load, and letting electrons go left to right the way they would spontaneously be pushed, what if I were to put in an external source of power? And that's often represented by these parallel alternating lines of alternating length. And I was to pump electrons the way in the direction they would not spontaneously flow. So I were to pump electrons this way. What would happen? And you can think about this as you're pumping water uphill. Water would naturally flow downhill. We're pumping it uphill. Well, I can just change the direction of these arrows here. And I would find that bromide over here in the right-hand half cell, bromide ions would be oxidized to form to release electrons and form bromine, and copper ions would be reduced by gaining electrons to form metallic copper. And I'll just change the sign of my arrow. This is now an electrolytic cell. It's a non-spontaneous reaction. We need an external power source to cause this reaction to occur. The cell potential now is negative. I'll change that like that, and now we've got an overall negative cell potential, and it's negative because, well, it's got to be negative for a non-spontaneous reaction. The delta G value would be positive. Or I could say, well, now since this is a reaction that's actually the oxidation, I can flip that around, and that means subtracting 1.09 from 0.34. And as I pump electrons that way, I would see metallic copper plating onto this electrode. I would see the blue color of my copper ions starting to fade as they are consumed. Over here, I would see perhaps a little stream of liquid bromine that would smell an awful lot like chlorine, a familiar smell to those of you who might be swimmers or play in a pool. Bromine and chlorine will obviously smell pretty similar since they're both halogens. And I would be using up bromide ions. I'd have a hard time seeing that since bromide ions are colorless in solution. But this would be the overall, well, I'm going to go ahead and write this in the direction it will actually happen. So what I would see is that copper ions would react with bromide ions to form metallic copper and bromine. And this would be the net ionic equation for the non-spontaneous reaction that is occurring. In practice, we can actually do this a little bit, make this a little bit simpler. Remember when we had the galvanic cell, the reason we had to have two different half cells was that we could not let the bromine come in direct contact with the copper metal. If we were to add bromine to copper metal, they would react without forcing the electrons to go through the wire. Since this is a non-spontaneous reaction, we can really do this in one cell, one electrochemical cell, and you'll see a picture of that in the notes. So we might just have our, draw this a little bit bigger, our beaker with our solution, and our solution might have copper ion in it and bromide ion. And then I'll have two electrodes. And an electron pump in here, so. And I should mention that, well, here's my power supply. It's going to be a source of voltage or current. What voltage does it have to be? Well, the minimum potential would be the difference between these two. So because the cell reaction has a potential of negative 0.73 volts, I would need a power supply of at least 0.73 volts in order to get a current to flow. And if I were just 0.73 volts, the current would be very small and really not get much of anything. So I would, in practice, want to use a higher voltage, a higher potential power supply, but it needs to be at least that voltage that would give me let the reaction go. My stoichiometric considerations are exactly the same as if this were a galvanic cell. So if I were to measure the current, and if I knew that a current of 2 amperes ran for 1,000 seconds, well, I know I would have transferred 2,000 coulombs of charge, and as a chemist, I'd be more interested in moles of electrons, so I would divide that 2,000 coulombs by Faraday's constant, get some number of moles of electrons, and then use stoichiometric considerations. And we'll practice that in just a minute. But in this particular case, electrons would flow down into that wire and out of this wire. And over here, I would get a reduction, and the thing that would be reduced would be the copper ion, forming copper atoms. And over here, our bromide ions would be oxidized to bromine molecules plus 2 electrons. As this current flows, I would see metallic copper plating onto my platinum electrodes, and it'd be kind of unusual to plate copper onto platinum, but that's what would happen. And over here, at this platinum electrode, I would see some pure liquid bromine streaming down, and since the bromine is probably not very soluble in water, I might get a little pool of bromine here. Eventually, some of the bromine might diffuse to the copper and react, but that wouldn't be really the concern. It would be in a galvanic cell. So, an electrolytic cell will always have a reduction and an oxidation. And part of the challenge for AP chemistry is to figure out what these half reactions will be, given your table of standard reduction potentials. Now, the fundamental principle is the thing that will be reduced is a thing that is present in your solution, in your mixture, that is most easily reduced. So to know what the reduction, what it's going to be reduced, we start at the top of our table and look at the species on the left-hand side, and when we get to something that is present in our solution, and in this case we got copper ions, that is the half reaction that will correspond to the reduction. To decide what is oxidized, we start at the bottom right, to the right-hand side of the arrow, because these are species that will lose electrons, and the ones at the bottom are the things that most easily lose electrons, and we start going up, and I don't really have any zinc or cadmium or hydrogen gas. I don't have any copper ion present initially in my solution, but I do have bromide ion, so the bromide ion is the species that will be oxidized to form bromine. And I've got those two half reactions here. And that's really it, almost. There is one complication that I should address, and that is that often these reactions are run, certainly if you've done this in a lab, you probably did this in aqueous solution. And since water itself can be reduced or oxidized, we have to be a little bit careful because sometimes the thing you get might not be the thing you think you might get, if you follow that. So let me try to illustrate that by working a problem where instead of having a solution of copper bromide, we have a solution here of sodium bromide. So sodium bromide would be a white crystalline ionic compound. You couldn't tell by looking at it. It looked just like sodium chloride or sodium nitrate or anything. But when it dissolves into water, it will give us sodium ions and bromide ions. As I start now to pass my current, well, as you might guess, over here, since I've got bromide ion present, I already know that those bromide ions will be oxidized to bromine molecules and release electrons, and those electrons will be coming back into the power supply. What's going to happen, though, at the cathode, where the reduction is going to occur? You might be very, very tempted to write, well, copper ions were reduced, so I've got sodium ions. The sodium ions will gain electrons to form metallic sodium. And maybe you'll write that, and that's not terrible, but if you've been around chemistry for a while, and most of you have, I hope, that's a little bit disquieting because you know that sodium, everyone knows that, not everyone, but if you throw a chunk of sodium into water, it reacts pretty violently. So it's unlikely you're going to form sodium in aqueous solution. And remember that a solution of sodium bromide not only has sodium ions and bromide ions, but also has a lot of water molecules. In fact, probably has more water molecules than anything else. So water itself can gain electrons, and if we go to our table of standard reduction potentials, and we start at the top and we start coming down, well, before we get to sodium, we get to this reduction of water with a potential of negative 0.83 volts, and that is the species that is present that is most easily reduced. So instead of sodium ion being reduced to sodium atoms, we would see water molecules being reduced to form hydrogen gas and hydroxide ions, so the solution becomes more and more basic. And now, if we wanted the overall ionic equation for that, again, there's a 2 electrons lost, your gain, and 2 electrons lost, so we can combine these pretty straightforwardly. I get 2H2O plus 2Br minus goes to H2 plus 2OH minus plus Br2. Notice that this reaction is balanced in terms of both particles and charge. I've got a net charge of negative 2 on the left and negative 2 on the right. And this time I would see bubbles of hydrogen gas coming up from this electrode. If I had some phenolphthalein solution in there, it might turn pink in this neighborhood because the hydroxide ion would turn the phenolphthalein acid-base indicator pink. And over here I would see the bromine, again, being formed as a not very soluble liquid in water solution. So anything below the reduction potential for water will not be produced in aqueous solution. And that means sodium ions and magnesium ions or magnesium atoms and all those very, very active metals. Conversely, anything that shows up above water or above the reduction potential for oxygen, which would be the oxidation potential for water, would not be oxidized. So if I had, let's say I had a solution of copper fluoride, if I were to start this with a solution of copper fluoride, I'd have copper ions and fluoride ions, or copper sulfate would probably be a more practical an easily obtained compound, which would do the same thing, but we'll use copper fluoride here. I know copper ions would be reduced, so when I start to pass my current, copper ions would gain 2 electrons to form copper atoms. And again, if you remember, bromide ions were oxidized, and you might be tempted to write that fluoride ions would be oxidized to fluorine molecules. And fluorine is not a very pleasant substance to work with. There are about a handful of chemists known as the fluorine martyrs because they actually died trying to be the first person to isolate pure elemental fluorine. So this stuff doesn't really show up, and this hugely positive reduction potential is probably a good indication that that doesn't happen. So what does lose electrons? Well, here we have water, and again, we're in aqueous solution. So what would happen over here is not the oxidation of fluoride ion, but the oxidation of water to form oxygen gas, 4 protons, and 4 electrons. And this would be our oxidation half reaction. If I want to combine these 2 half reactions into an overall reaction, I have to now acknowledge that I've got 2 electrons being gained and 4 electrons being lost. So I would need to multiply this whole thing through by 2. And my overall balanced equation would be 2 copper ions plus 4 electrons. I'll go ahead and write them for now. Plus 2 water molecules reacting to form 2 copper atoms plus 1 oxygen molecule plus 4 hydrogen ions plus 4 electrons, and of course those electrons better cancel those electrons, and I'm left with a net ionic equation. And once again, notice the total charge is the same on both sides. 2 times plus 2 is plus 4, and 0, here we've got 0 and 0 and 4 positive ions over there. And you can figure out what would happen with sulfuric acid or any other species here. If you did want to electrolytically form sodium, well, you couldn't do it from aqueous solution, and in practice what you would need to do is do it from a molten salt, an ionic salt that has been heated up to the point that it would liquefy. Okay, so that's the principle. Let me go over just a couple of problems here with you, and I think some of them have been gone over already. So if you have the notes and some practice problems that maybe your teacher gave you, whether you want them or not, you're asked in problem 1 to write the net ionic equation for the electrolysis reaction that occurs in each of the following cells. And we're asked about a direct current is passed between inert electrodes immersed in a aqueous solution of copper 2 bromide, and that's the one we kind of started with, copper 2 bromide, so Cu2 plus Br minus, 2Br minus, and this is aqueous. The species that is reduced is a thing I get to first when I come down here, and that's copper ion, so my reduction is Cu2 plus 2 electrons going to Cu naught. The species that's oxidized, well, I'll start from the bottom right and go up, and I don't have anything, none of that, none of that, none of that. Whoop, I got bromide ion, so I've got 2 Br minus, goes to Br2 plus 2 electrons, and we just combine those. I got 2 electrons and 2 electrons there, so they combine fairly straightforwardly. I don't have to multiply, and my overall ionic equation is copper ion plus 2 bromide ion forming copper atoms and 1 bromine molecule. And again, this is a non-spontaneous equation. The E0 here would be negative 0.73 volts, and the delta G would be negative 2 moles of electrons per mole of reaction, that 2 come from there, times 96,500 coulombs per mole of electrons, times negative 0.73 joules per coulomb. Remember, a volt is a joule per coulomb, and moles of electrons will cancel, coulombs will cancel, and I'm going to get a positive number because this negative sign and that negative sign will eat themselves up, and since this is a non-spontaneous reaction, I would expect a positive number for delta G. Remember, your unit here will be joules per mole, and a pretty big number, so traditionally, or conventionally, you would express that in kilojoules per mole and divide through by 1,000. If we had a solution not of copper bromide, but of copper sulfate, well, we don't have any bromide ions present. I'll leave the copper up there since I know that same thing will happen, the sulfate. And now I want to look and see what's going to be oxidized. Well, I can't find sulfate anywhere on the chart. In fact, sulfate is not very easily oxidized at all, but we are in aqueous solution, so we will put the oxidation of water. So I need my 2H2O, or I've got to turn this around, forming O2 plus 4H plus 4 electrons. And now I'm going to, again, need to multiply this by 2 so that those electrons will cancel those electrons. And I get what I had earlier, no surprise, I get the same reaction, whether it's copper sulfate or copper fluoride solution. Copper ions plus 2 water molecules going to copper atoms plus oxygen molecules plus 4 hydrogen ions. In this case, in my delta G equation, the N would be 4 moles of electrons per mole of reaction. If I had now 2 more quick ones, a solution of sodium sulfate, I've got sodium ions and sulfate ions. I already looked for sulfate. I know it's not going to show up over here, so my oxidation will be the oxidation of water, 2H2O, going to O2 plus 4H plus 4 electrons. I know for sodium, well, when I'm looking at the reduction, I'm going to get to water before I get to sodium. So water, in fact, will also be reduced. And this time I'll get my 2H2O plus 2 electrons going to H2 plus 2OH minus. And now I need to combine both of those that need to balance electrons. So 2 electrons there and 4 electrons there. I will multiply the top equation, half reaction, by 2. And that will give me 4H2O plus 4 electrons plus another 2H2O. Those are all my reactants. On the product side, I'll get 2H2 plus 4OH minus plus O2 plus 4H plus 4 electrons. And now we've got to do a little bit of canceling, a little bit of chemistry. First, the 4 electrons cancel. But now, and I've got 4OH minus and 4H plus, and you should recognize this is a base and an acid, and that they will combine to form 4H2O molecules, and those 4H2O molecules will cancel out those 4H2O molecules. So my overall net ionic equation is just 2H2O going to 2H2 plus O2. There you go. And easy to do. You can do this with a 9-volt battery and a couple of pencil leads in a solution of sulfuric acid or sodium sulfate. And then finally, let's look at, be careful, not everything is done in aqueous solution. If you have, for example, inert electrodes in a solution of molten sodium chloride, so now you've got Na plus and Cl minus, but there's no sodium, there's no water in there, so the reduction will have to be the thing that's reduced, and there's no way a chloride ion is going to pick up another electron. So in this case, we do form sodium metal, and it's not on the chart I have over here, but it should be the one you have at home. We would form chlorine gas, and 1 electron, 2 electrons, so this gets multiplied through by 2, and our overall reaction would be 2 sodium ions plus 2 chloride ions goes to sodium metal plus chlorine gas. And that would be the electrolysis or the electrical splitting of sodium chloride. And these are how you'd figure out what the reaction that occurs in an electrolytic cell. I want to do one more problem that's a little bit more quantitative, and we'll use the current. So you've got a direct current power supply and 2 famously inert electrons in an aqueous solution of chromium-3 sulfate. So let's put a little picture here. We've got Cr3 plus and 2 of those, and some sulfate ions, SO4 2 minus, SO4 2 minus. We have 2 electrodes, and we've got our power supply that looks like that. And we're told that metallic chromium is forming over here, and that bubbles of a gas are being evolved over there. So the first question asks us to show the direction of electron flow in the wire, and that will help to know what's happening. You're given 2 half reactions, and since chromium is being produced, we know that the chromium will appear as a product, and that means chromium, this is the chromium ion over here, will be gaining 3 electrons to form chromium metal. So since electrons are being gained over here, electrons are going this way through the external wire, from the power supply that way. Identify the gas produced at the electrode. Well, something's going to be losing electrons over here and producing a gas, plus some number of electrons. And, well, what do we have in the solution? Nothing here except for water. Sulfate ion is not there. So over here, 2H2O is going to O2 plus 4H plus 4 electrons. So these bubbles would be going up. The pH of the solution should be decreasing since we're producing an acid there. Part C of this asks us to write the balanced net ionic equation for the overall electrolysis reaction that occurs as a cell operates. In other words, combine these 2 half reactions, being careful to cancel electrons. 3 electrons consumed, 4 electrons produced. The least common multiple is 12, so I need to multiply that by 4 and multiply this whole half reaction by 3, whole half reaction. And what I get when I do that is, let's see, 4 chromium ions. I'll go ahead and write the 12 electrons explicitly. Those are all my reactants from here. Plus 3 times 2 is 6 water molecules producing, and I don't think we need this anymore. Producing 4 chromium atoms. 4 atoms of chromium, and then 3 oxygen molecules, 12 hydrogen ions, and 12 electrons. And we'll just check that the total, well, first we'll check the electrons cancel, which they better, since we carefully multiplied by 3 and 4 to make sure that would happen. And now we need a total charge that's the same on both sides. 4 times 3 is plus 12, and 0. 0, 0, and plus 12. So that looks pretty good. Predict the plus minus sign of the E cell and delta G. And since this is a non-spontaneous reaction, E cell is negative and delta G is positive. And again, because this is a non-spontaneous reaction, we are causing this reaction to occur. The values of E cell and delta G are going to be from the reduction potentials given here. So remember, you do not multiply potentials by these multipliers here because that's in joules per coulomb. So E cell would actually have a value here of negative 0.54 volts minus positive 1.23 volts. And let's see, 0.54 minus a positive would be negative 1.77 volts, if I did the arithmetic correctly. And the delta G naught value would be negative 12 moles of electrons per mole of reaction times 96,500 coulombs per mole of electrons times negative 1.77. And I'm going to write that volts as joules per coulomb. So I can cancel coulombs and moles of electrons, and I'm going to get an awfully largely positive number of 1,970,000 joules per mole of reaction, and that's a positive number, or 1,970 kilojoules per mole of reaction. All right, a little bit of stoichiometry and then we're done. If the cell operates by passing a current, and remember current is in amperes and those are coulombs per second, so if you've got a current of 2.4 amps for 30 minutes, well, our charge passed would be 2.4 coulombs per second times 30 minutes would be 1,800 seconds, and that would be 4,320 coulombs of charge. Nice, perfectly nice unit if you're doing physics, not so useful if you're doing stoichiometry. We'd much rather have moles. So the next step will almost always be calculating the moles of electrons, which will be 4,320 coulombs divided by 96,500 coulombs per mole of electrons. And that gives me 0.0448 moles of electrons. Goodbye thermodynamics. Hello stoichiometry. And that's good. And now I just need to figure out the mass in grams of chromium deposited on the electrodes. Well, my half reaction for chromium was Cr plus 3 electrons going to Cr naught. And this gives me a 1 to 3 mole ratio between chromium and, or 3 to 1 between electrons and chromium atoms. So my delta moles here is minus 0.0448. So I'm going to form 0.0448 times 1/3, or I did this 0.0149 moles of chromium. And if the problem stopped there, I could stop there, but it asks for the mass in grams. So I will take the mass of chromium would be 0.0149 moles times 52, is it? 52 grams per mole. And that would give me 0.776 grams of chromium metal. And again, we're just doing stoichiometry, so mole relationships are going to be important. Often you'll see these equations combined with, or these problems combined with something else. In this case, since we're producing oxygen gas, a gas law problem might be appropriate here. And you might be asked to calculate the volume of gas produced at 25 degrees Celsius and 1 atmosphere. Again, our half equation was 2H2O going to O2 plus 4H plus 4 electrons. We still have the same number of moles of electrons, was 0.0448. So change in moles, 0.0448. So the moles of oxygen would be a 1 to 4 mole ratio. Moles of O2 would be 0.0448. There are lots of ways to think about this. Moles of electrons times 1 mole of O2 for every 4 moles of electrons, and that would be 0.0112 moles of oxygen. And if the problem asks you for moles of oxygen, you would stop there, but we want to know the volume of gas produced. So V equals nRT over P. Here's our N, 0.0112 moles of oxygen times R. There are lots of expressions for R, but since we're given the pressure in atmospheres, probably the most useful is 0.0821 liter atmospheres per mole Kelvin times our temperature, 25 degrees Celsius. Let's remember that that better be in kelvins for this particular use, divided by the pressure of 1.20 atmospheres. And now you get the satisfaction of canceling moles with moles, kelvins with kelvins, atmospheres with atmospheres, and being left with liters, which is good because we want a volume, and that works out to be 0.228 liters of oxygen gas. So that's it. I hope this was helpful. Good luck. If you have any questions, do email me or tweet me at AskLouKY, and enjoy AP Chemistry. Bye-bye now.